Swayam Prabha. Digital India. Educated India.
So, passivity, zero state observability for this system, okay. X dot is fxu, y equal to h of x. We are going to use this immediately to design stabilizing control. I mean, that's the theorem, okay, that's this theorem, okay. What does it say? It says that if the system that we just talked about is passive with a radially unbounded v of x, okay, no longer just v semi-definite positive. We are saying that the v is radially unbounded because obviously we want to use Lyapunov theorem, yeah. So, if the system that we just saw is passive with a radially unbounded storage function v of x and zero state observable, then any feedback of this form, okay, where phi is locally Lipschitz in y, phi is 0 at 0 and y transpose phi y is strictly positive for all non-zero y, this globally asymptotically stabilizes the zero state, okay. So, how do you construct the feedback? You basically declare the control to be any minus phi y with these properties, Lipschitz 0 at 0 and actually positive, y transpose phi y is positive definite, that is its, for non-zero y it is strictly positive, okay. So, a very nice result actually, I mean, and really useful, okay. So, let us just look at what happens, okay. We will look at the proof, yeah, in this case we will look at the proof just to see sort of what happens. So, so this v that we have, we are already assuming that for this system you have a radially unbounded v. So, we take this as the candidate Lyapunov function because it is already C1, right, and already radially unbounded. So, pretty strong properties there, and we take this as the candidate Lyapunov function for the closed loop system. So, the system now becomes this because I have plugged in my feedback, yeah, because it is minus, instead of control I have minus phi y because that is the feedback I have chosen, okay, and then the output is just h of x, yeah. Further, what do we know about this v of x? We know that the derivative, yeah, this is the passivity property itself, that partial of v with respect to x multiplied by this guy is actually less than equal to u transpose y, okay. And the funny thing is u is just minus phi y, so I plug this guy in, and by this assumption of positive definiteness, what do I have? That this guy is negative semi definite, okay, not negative definite, okay. Remember why? Because why is it not negative definite? Actually, I should not say because, you tell me why. Why did I say this is only semi definite and not negative definite? The same thing I say every time, almost in every class. Why is this v dot only negative semi definite? What did I do? I took the partial of v multiplied, absolutely, thank you very much, yeah. It does not have the entire state x, it only has y which is less, yeah. So, if you do not have all the states, cannot be definite at all. By our assumption, it is sign definite but not positive definite, okay. It is only negative semi definite, alright, excellent, good. Now, we are ready to apply the Barbashine-Krasovsky-LaSalle theorem, okay. Now, you remember why this zero state observability looks very much like the LaSalle invariance condition, right, because of this, because we are going to invoke that, because we started with a radially unbounded v, but we ended up with a only negative semi definite v dot, right, and in all such situations we invoke in some version of LaSalle's, yeah, whether it is the original LaSalle invariance or it is Barbashine-Krasovsky-LaSalle. In this case, we are looking at the stability of the origin. So, it makes sense to use the Barbashine-Krasovsky-LaSalle. We are not dealing with limit cycles and all that complicated stuff. We are talking about stability of the origin. So, no need for the original LaSalle, no need for the omega and all that. All we need to do is have a radially unbounded v, excellent, we do. Have a negative semi-definite v dot, we do. Next step, construct the set V dot equal to 0, and that is exactly this guy, phi transpose y equal to 0, that is guy this, yeah, and this is I am claiming that this is actually equal to y equal to h of x equal to 0. Why is this equal to this?
Because we have taken for y not equal to 0, y transpose y, y transpose y is less than 0.
Absolutely. For any non-zero y, this is strictly positive. So, if this is actually 0, the only way that is possible is if y is actually equal to 0. Okay? That is why these two are the same, alright, just by our assumption, nothing bigger than that. Excellent, right. And so, by 0 state observability, because this is now that set that we discussed in the 0 state observability, right, exactly. So, in fact, it almost looks like we have defined things and assumed things so that everything works out, yeah, alright, but these tend to work out a lot of times, it is quite amazing, you will see some examples. So, yeah, so a lot of times these assumptions do get satisfied is what I am saying. When I am stating the theorem, it looks like I made some ridiculous looking assumptions just to make sure that my theory gives me a stabilizing controller, but that is not the case, you will see it works also at times. Okay. Anyway, let us look at this. So, this is the 0 state observable set. What do we know? We know that no solution but the trivial solution will stay in this set, okay, when control is 0, when control is 0, remember. Okay. So, let us look carefully what happens. In this set, y is equal to 0, right, which means the control which is phi of y minus phi of y is actually minus phi of 0, right, and that is 0. Okay. So, on this set control is 0, okay, which means we are already looking at the uncontrolled system, okay, and we already know by 0 state observability assumption that for the uncontrolled system only the trivial trajectory is inside here, nothing but the trivial trajectory. So, we are done. This is what we need in Barbashine-Krasovsky-LaSalle, right, that the largest invariant set inside E has to be nothing but the 0 trajectory. Okay. So, we have just completed the arguments, alright, is that clear? Pretty straightforward proof actually, make sense? Okay. Alright. I do not know what I have written on the sides here. Let us not worry about this, yeah, you do not have to worry about this, that is fine, okay. We will look at that later, alright. Now, I already said that it looks like we made up these assumptions so that things go through and all that, and it is true to some extent, but there are ways to make sure that this goes through, these assumptions are getting satisfied, okay. One of the methods is passivity by output selection. In a lot of systems that we are designing controllers for, there may not be real outputs, okay. We might have the flexibility to choose outputs so that you have the passivity property with respect to that output. Remember, passivity is a property which is somehow related to input and output, okay. So, but if you have the choice of choosing an output, you might be in good shape, okay. So that is sort of one of the things, right. I mean, I think that is what is an example I am trying to give here in a very messy handwriting, unfortunately. For example, if you just an example, if I take this system, this is the standard integrator type system we have been looking at in backstepping. So, I hope you recognize this system already very quickly. Yeah. In backstepping, you would take x2 is minus x1, then you will take CLF as x1 plus x2 plus x1 squared, and so on and so forth. Yeah, you are used to that. For passivity, what I am going to do is, I am not trying to construct a a CLF or anything as of now, right, because we want to use Barbashine-Krasovsky type ideas. So let's see, I will choose my measurement as the position or the x1 state. Okay, if you think of mechanical system, it's the position state. Okay, I just measure one state x1. What happens? So the question is, can you choose a V appropriately? And this is what we have to sort of think about carefully. I am not sure if I have actually given a V choice here. I want this V dot to be less than equal to U transpose Y. Okay, and that is anyway, in this case it looks like I did not actually make the choice proper. I think actually let me come back to this later. Okay, I did not make this choice properly yet. Okay, this is not a complete problem here. Okay, I will get back to this later, but the point is, if you have such a system, there are ways to sort of use output selection like this to make it passive. Okay, that is the whole idea. This is not a completely worked out example, so I am not going to look at this right now. Okay, let us not worry about it, but let us look at the theory first and see what happens, because there is already another nice example here. Okay, right. If you have this kind of a system, right, which is again a control affine system, yeah, and as usual you have some states, some control, Lipschitz in X, and you further suppose you have that your drift system is stable. Okay, not asymptotically stable, but stable. What do I mean by that? That partial of V with respect to x times f of x is less than equal to 0. Okay, this is actually this is basically stable unforced system, or it's basically you are saying that without the control the system is at least stable. It is not asymptotically stable, not going to converge to the origin or anything, but it is at least stable. It is not going to escape or anything. Okay, great. If you have that, then you can choose your y as this, okay, to make the system passive. Okay, do you understand why? Because of this. Yeah, if I take the same radially unbounded function v, okay, and I take its v dot along the entire trajectory, not just the uncontrolled trajectory, the entire trajectory, I get this. Yes, it is just del v del x fx del v del x gxu. Okay, and now I am saying that I want this to be less than equal to y transpose u. Okay, so I am basically artificially choosing this as y itself. Okay, why? How did I get from here to here? The first term is less than equal to 0, right. So I can pretty much forget this guy. Okay, therefore I know that this is less than equal to this much. Okay, now if I choose my y transpose as the first piece, then I am done, right. I have my passivity property. Okay, this artificial looking property, it's just by choosing an appropriate output I have this passivity property. Okay, again might seem artificial to you, but the point is, if you have the freedom of choosing the output and your aim is just doing control design, it's not this y, I do not want you to think of it right now as the actual measurement from sensors and things like that. You just think of it as a tool to design your controller. Okay, once you have designed your controller, you can figure out how to implement it and all, that is a later matter, but right now you are just using this y, even if it looks artificial, it is just a way of designing a control law for you. Alright, okay, great. Now so we know that this sort of a choice for y will make the system passive. Okay, good. So what is the example? This sort of example. Okay, again not too far fetched, not too far from this way. Yeah, I have just given a particular form for the drift term here, that is all. Yeah, it is not too far fetched from what we already have. Yeah, now let us look at this v of x, which is why did I choose this form, is because this is actually making the system stable. Okay, so you are trying to make the system stable also. Yeah, suppose I choose my v as x1 to the power 4 over 4 plus x2 squared by 2. Okay, why did I choose instead of square in both, fourth power in one and square in the other? Anybody? because there is an x cubed, just to cancel this x cubed term. Yeah, if you take the derivative, what happens? Yeah, if you forget the control and you take the derivative, it comes out to be 0, exactly 0. Yeah, that is why I chose the x1 to the power 4 instead of x1 squared, just to cancel this x1 cubed term. Okay, make sense? This is how we keep manipulating early Lyapunov candidates. This is a pretty good idea. Okay, great. So v dot turned out to be 0 and v was radially unbounded. What does it mean? That the unforced system is stable or uniformly stable in the sense of Lyapunov. Okay, okay, great. Now I want to make the system passive, right? Now what do I need for the system to be passive? I need this to be less than equal to u transpose y. Yeah, but in this case the right hand side was 0. All right, so I am free to choose any y actually, right, because the right hand side is pretty much 0, right? V dot turned out to be 0. So v dot less than equal to u transpose y means I can choose pretty much, you know, wait, did I get this correct? V dot is 0 plus x2 times u. Okay, yeah, that's fine. So that's fine. This is stable. So basically, what am I choosing as my y? I will just go back to this formula. I think it's better that I go back to the formula. What does this formula give me in this case? What is g of x? Yeah, there is no g of x, just identity 1. Okay, and what is so again I have to be careful. G of x is not 1. What is g of x actually? G of x for this example is 0, 1. Yeah, it is a second order system, so we have to be a little bit careful. Okay, what is partial of v with respect to x? Yeah, partial of v with respect to x is this. In fact, whatever, I mean it depends on how you want to look at it, but typically I take gradients as row vectors. So what is this formula? Give me, it gives me what? It just gives you y equal to x2, right? Partial of v with respect to x multiplied by partial of v with respect to x multiplied by g of x is just x2, right? So what our claim is that the system is passive with y equal to x2. Okay, okay. On top of this, in fact, it turns out that in this case my system is also 0 state observable with this y. How do you claim 0 state observability? Unfortunately, I cannot pull it up, but yeah. How do you claim 0 state observability? What do you need to check? Yeah, in the set h of x equal to 0, only the 0 trajectory exists. So here what is it? What is the set h of x equal to 0? It is x2 equal to 0. Okay, and then I am sort of invoking LaSalle invariance type ideas. Yeah, similar ideas, right? If x2 has to be 0, what is the largest invariant set inside x2 equal to 0 set? x2 dot also has to be 0. That is how we do it, right? And if x2 dot has to be 0, what is my dynamics? x1 dot equal to x2. Sorry, x2 dot equal to 0, right? I just proved x2 dot equal to 0. I need x2 dot equal to 0. So if x2 dot equal to 0, if you look at the dynamics of x2 without the control, because we are talking about the uncontrolled system solutions, we are not talking about the for the uncontrolled system, if x2 dot has to be 0, then x1 also has to be 0. That is the only way. Yeah, because if x1 is non-zero, and anyway there is no control, then x2 will move away, right, from the 0 value. Therefore, you cannot stay in this set y equal to 0. Okay. So, the only way this can happen is if x1 is also 0. Therefore, we have just shown that the largest invariant set inside y equal to 0 is both x1 and x2 equal to 0. All right, makes sense. All right. So, this y is not just giving us passivity, but also 0 state observability. So, you know pretty much immediately that I can apply this theorem. Okay, I can apply this theorem to construct a asymptotically stabilizing feedback, not just stable. The system has stability, but if you want asymptotic stability, you can immediately use this. Okay, essentially you just need a function of y. What is in this? What's it in this case? Is just a function of x2. Yeah. So, that is the cool thing, interesting thing, if you may, that you only need a function of x2 in the control, you do not even need the first state. Yeah. So, if you were a control engineer or a practitioner, you can pretty much say that I only need to measure velocities to implement a controller for this system, because it is only a function of x2, because I just so basically if you think about it, what would I choose as my control? My requirement for the control are that phi is Lipschitz, phi 0 is 0, and y transpose phi y is strictly positive for all non-zero y. Okay. And in this case we have chosen y is x2. Okay. So, what is it? I just choose my control as this guy, just minus k x2 for example. Yeah, I know that this is at 0 value of output, control is 0, right. I also know that y transpose phi y is basically just k x2 squared, in fact. Yeah. Okay. So, therefore, it is strictly positive, I mean it is 0 only when the state is 0. Okay. Therefore, this is a valid control, and that is fine. I mean it is just looks like a this becomes the control now. Yeah, as a function of the state x2, this is the controller. Okay. But I can do even better, I can actually design a saturated controller, which is again something that lot of engineers care about, that the control does not have large magnitudes. So, all I need to do is I need to satisfy these properties, right. So, what will I do? Instead of choosing k x2, I take k tan hyperbolic x2. What does the tan hyperbolic function do? It takes any argument and it fits within plus minus 1. It is a saturation function. Yeah, it is a smooth saturation function. You can also have non-smooth saturation function, like this can be a non-smooth saturation function, but this is sort of a smooth saturation function. Okay. So, instead of taking minus k x2, I can take minus k tan hyperbolic x2. All right, and this is a very nice function, it is 0 only at 0. So, therefore, it satisfies this property also, right. It is actually it maps exactly, like if your y is like this, then this becomes like this. Yeah. So, it never it is like this. Yeah, when y is positive, tan hyperbolic y is positive, when y is negative, tan hyperbolic y is negative, it is 0 only at 0. It is actually a sign, a mapping which maintains the sign also. Yeah, so, it is a very nice mapping, it is just saturating it. Okay. So, minus k tan hyperbolic x2 is also a saturated control choice that you can do, and in that case your control is just lying between these two. Yeah, it is flipped just because of the negative sign, that is all. Okay. So, if you have the ability to choose an output, yeah, which will make the system passive and also 0 state observable, then you can directly apply this result. Okay. So, in this case also, for a system like this also, for a very general case like this, you will have to think. It will not, see in this case what did we have? We sort of assumed that your f of x is a stable system, gives you a stable system. Okay. In this case, that is not evident that this system is going to be a stable system or not. Okay. If it so happens that this system turns out to be a stable system in the sense of Lyapunov, then of course you can apply the same result. All right. Otherwise, you have to figure out how to play with these terms. Okay. And that is what we will see in the next sort of trick, if I may. Okay.